Lesson 7.3, our last in Chapter 7, estimating a standard deviation or a variance, right, is the name of the game. Our keys, we are going to work using our sample standard deviation to get to our population. Yes, that's the difference between these two. And the big deal here is that now, as opposed to the last two sections, our distribution is asymmetrical. And that's going to pose a little bit more of a work. All right. So we are using a non-symmetric distribution to estimate the standard deviation or the variance. All right. And as you would expect, S squared is the best estimator of the variance, square root of the population. So this distribution has a funny name. It looks like x squared, but that's not how you're gonna pronounce it. It's actually pronounced as chi-squared. If you look it up online, this is actually, when you spell it as the Greek letter chi, C-H-I, and so you would look for chi-squared distribution. All right, here is the formula for that distribution. Obviously, I'll reuse the variance in both the sample and the population there. Notice also degrees of freedom shows up here, n minus 1. Okay? There's what it looks like. Notice it is skewed left. We kind of saw this back in Chapter 6 when they introduced it to you. And as you increase your sample size, yes, as your degrees of freedom increases, it becomes more and more normal-ish. One other thing to note is we have all non-negative values. So notice 0, which used to be in the middle, is sitting off to the left side. So chi-squared is always positive or 0. Important note. All right. We're going to find critical values on that distribution, which will separate that which is significant from which that is not. Okay, we call these, again, the tails. So they're going to look like right here, and it's going to be all this area and all this area. Okay, and you're going to be looking for those particular values depending upon the level of confidence that you want. Let me bring the radio down just a titch. All right. Mainly tables. Again, technology, I'll put out a little video showing you how to do that with StatCrunch. Our degrees of freedom, n minus 1. The values, again, of chi-squared are always greater than or equal to 0. As n increases, the distribution becomes more normal, is more normal, or normalizes. I suppose I could have used that word. Because there is no symmetry to the graph, you can't have a plus or a minus. So this is the first bit of bad news that we've got. So the way we write things out, instead of the old format of saying our parameter plus or minus the error, we now have our lower limit and then our upper limit. Okay? Or you can write it out as just an inequality with mu sitting in the middle. All right. So let's dig into an example here. Find the tail areas using 22 IQ scores. It seems to me this had to do with lead in pipes, and they were looking at, they broke people up into high levels of lead exposure, medium, and none. This, I think, is the middle group, which is where this data is coming from. So we want to know what is the confidence interval for our standard deviation, with a 95% level. By the way, if you're watching the news at all, lead in water systems is kind of a big deal across the US because houses were traditionally built with lead pipes, and so older cities tend to have those systems still in place. The most notable is Detroit, and some cities have been neglected over other cities in terms of replacing and changing them. All right, that's the little background to this problem. So we got our degrees of freedom here. We see it's 21. And again, taking our confidence level, breaking that down into the tail areas. Now this is where it gets tricky, not on the right side, okay? So first of all, here is how we label the right tail of chi-squared, okay? And that is 35.479. That'll come from the table in just a moment. Actually, let's go there right now. What the heck? Okay, so I did a little Google search here, and chi-squared table, you can see that up there. I'm gonna hit images, and let's open up any one of these. We'll say view file. Let's see if that opens it up. There we go. And again, here we have a 95% confidence. So that puts us in 1, 2, 3, 4. The column, which is fifth column over, and we're coming down to degrees of freedom, which is 21, and that's not on. Let's see if I can scroll down. It's not on my image. Okay, got to go back, grab a different one that I can pick up. This one looks like it's got it. All right, here we have 21. So it's got 20 and 22 on this one. That's a bummer. No, that one doesn't have it. We'd have to interpolate. We could interpolate, but I'd rather not. Here we go. Let's see if this one opens up. All right, so now we are in column, the third column over, yeah? And you can see there at the bottom, it says 10.283 for 97.5. And if you go over to let's see, 1, 2, 3, 4, 5, 6, 7, 8th column over, and the 21th row, you can see that value that we're looking for, 35.479. So if I come back into here, there you see those two values. Now you may be asking yourself, where the heck did I get this particular value of 10.283? There's a little wrinkle here, and that is that when you're doing the left tail, you have to find the critical value, first of all, using accumulated area. This is weird, I know, but to the right of that shaded region, of that critical value, okay? So it's always area to the left. And again, because it's 0.025, then it would be 0.975, which doesn't sit right with how we've been doing it in the past, but that's how the table works. All right, there we are. Bam, throw them into the interval. There's our confidence level, okay? So the steps of constructing: verify your requirements. For simple random sampling, and obviously if our distribution is normal, it must be. Notice there's no requirement here of also n is greater than 30. No, 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 no. No, we've got to have a normal distribution. Didn't mean to erase that. Highlight it. All right. Find the critical values using degrees of freedom and the confidence level. Again, table or technology. Technology is probably going to be faster. The formula for sigma squared is n minus 1 s squared divided by x squared r. Notice here in this formula, I'm going to highlight this here. We have r and l on the wrong sides, unquote. It feels like the wrong sides, but because you're dividing by a smaller number, the critical value that's on the right side should be bigger, correct? And the value that's the larger one in the denominator would naturally then be on the smaller side, because that's going to make the number smaller. Hopefully that made some sort of sense, that you saw kind of the contradictory nature of that, but that's why it is that way. And again, that'd be if you do it by hand, using the particular values that you have. Technology, again, would tell you straight up what those values are. All right, again, if you start with the variance, but know that we are looking sometimes for the standard deviation, so you got to take a radical of everything. In this case, I'd take a radical of each of these sides, so to speak. There is a round-off rule. Use same as last time. If you're using the original data set, go +1. If you're using the summary data, then the same decimals as the given values. So here we go. IQ scores, bam, standard deviation. Assume we have a 95% level that we're under, and simple random sampling, construct, bam. Our confidence interval 4, pay attention, this is the standard deviation. All right. Item number 1, does it meet all the requirements? Yes. This is a normal distribution, and it's a simple random sampling. Number 2, degrees of freedom, 21. Establishing our critical values so that we can look up then in the table what they correspond to on the chi-squared distribution. And we did that earlier, correct? So now I can come over and plug those values into my formulas. Again, 21 times that squared, 21 times that squared. Again, notice dividing by the larger number gives us, in this case, the smaller number, 120, and then divided by 10 gives us the larger number. Okay. So, using those values, we can then come down here, and again, we write our variance squared, take the square root to get it down to the standard deviation of 11.0 and 20.4. Okay? All right. Hopefully that made sense to you. So now we have a 95% level of confidence that given other samples of similar size, right, our standard deviation would be within the interval of 11.0 to 20.4. Finally, they look at to determine sample size. N, yes? We use a table. There isn't a formula here. It's typically a table that's a lookup table. And I think StatCrunch will do it for us. But my hunch is they're going to give you a table and just ask you to interpret. It's going to be pretty simple. But they've got to give you the confidence level. And then the other thing that they have to give you is what percent of error are you looking for, right? Are you allowed for your standard deviation? And so in this case here, we're looking for a 99% confidence level and a 10% error between S and sigma. So then we look in the table and we go, okay, let's see. Here's the 99%. This was a 95 above it. And so I'm looking for, come on in. We've got a 10% error, and we've got 336. So that's where I got the 336 from. Okay, there it is. That's the lesson today on estimating sigma and